Quantum state vectors, or QSVs, compose all of space-time. They are spinning arrows on a qubit. The projection of these arrows onto their neighboring qubits create interference patterns. These patterns encode the geometry of space-time itself. Bright regions of constructive interference signify areas of high information density, while dim regions of destructive interference represent voids in the quantum fabric. The orientation of the QSV defines instantaneous velocity components projected onto space-time. These components are encoded as holographic projections of the QSV's angle, theta, along the x and y axes. The universal benchmark for these projections is the speed of light. Angular frequency defines the instantaneous rate of rotation of the QSV. As curvature increases near massive objects, the angular frequency decreases. This stretching of angular frequency directly encodes time dilation into the quantum fabric of space-time. The speed of light transforms velocity into the angular frequency of the QSV spinning on the qubit. The speed of light uses itself as the ultimate benchmark for measurement. In the Lorentz factor, velocity becomes the angular frequency of the QSV. The curvature of space-time slows the angular frequency of QSVs near massive objects, stretching time itself. Einstein's field equations describe the curvature of space-time as arising from mass and energy. In quantum information holography, we enhance this by showing that the arrows of Einstein's vector tensor field are actually quantum state vectors, which simultaneously encode velocity components, probabilities, and curvature. The instantaneous orientation of each QSV defines velocity and probabilities, while curvature emerges as the geometric result of the QSV's rate of change or angular frequency. This unites quantum mechanics and general relativity, revealing the quantum origin of space-time and gravity. The curvature of space-time, represented as the rate of change of a quantum state vector on a qubit, is encoded directly in the quantum state vector tensor field as an informational hologram. Time dilation, velocity, and probabilities are unified in this enhanced framework, showing how Einstein's field equations arise from the quantum information encoded within QSVs. Quantum information holography reveals the deeper structure of the universe, where probabilities and geometry are one and the same. Velocity, time dilation, curvature, and gravity all emerge from the spinning quantum state vectors that compose the holographic screen. The holographic universe is not just observed. It projects itself into being, encoding the laws of physics within the dance of light, geometry, and information. The spinning quantum state vectors, or QSVs, project their velocity and probability components outward, forming ripples of light that interact with neighboring qubits. When these ripples overlap constructively, they create regions of high information density, glowing brighter on the Bloch spheres. These regions encode richer probabilities and define the structure of space-time. In regions where the ripples cancel each other out, destructive interference creates null zones, areas of low or null probability. This dynamic interplay of projections forms the geometry of spacetime. Constructive and destructive interference patterns curve the fabric of spacetime, creating the gravitational landscape. The curvature of spacetime encodes these probabilities directly. Information and geometry are one and the same, woven together into a holographic fabric. Interference patterns create not just the curvature of space-time, but also the foundation of reality itself. The holographic universe emerges as a perfect interplay of light, probability, and geometry. Each qubit on the event horizon functions as a holographic plate, encoding all possible quantum states of the universe. These plates are stacked together in a layered formation, like clear photographic negatives, limited by the Beaconstein bound, the maximum information that can be contained within a region of space. The singularity acts as a light source, shining through these plates. The light refracts, interacts, and combines with the etched quantum patterns, projecting a hologram onto the event horizon. One of the most fundamental holographic plates in the stack is the cosmic microwave background, the baby picture of the universe, just 300,000 years after the Big Bang. The CMB, an initial quantum probability holographic plate, encoded the seeds of all cosmic evolution. The cosmic microwave background is the foundational hologram of our universe, shaped by quantum probabilities and projected from the singularity. It is the holographic blueprint from which space-time, galaxies and stars evolved. The same plates, rearranged in a different order, produce entirely new projections or realities. This dynamic reshuffling of probabilities aligns with Feynman's sum over histories, where the universe's path is shaped by the quantum phases and frequencies encoded in these plates. In quantum information holography, the holographic plates embody Feynman's sum over histories. Each plate represents one possible quantum path, and the projection onto the event horizon is the sum of these paths, weighted by their phase and frequency. Quantum information holography's enhanced Schrödinger equation governs this evolution. By encoding probabilities in the orientation and dynamics of QSVs, it unites quantum mechanics with space-time geometry by describing the universe's growth from its initial holographic plate. The cosmic microwave background is a picture of the first holographic plate, which encoded the initial quantum probabilities after the Big Bang. Quantum information holography reveals the universe as a holographic projection where light, phase, and frequency shape the cosmic structure. The cosmic microwave background is the foundational holographic plate, the blueprint of the universe, projected and evolved through the sum of all quantum paths.